All right, I think we should start. So I'm Christian Kadar. I'm from Imperial College London. I'm chairing this very interesting and important, very interesting session on an important topic, vulnerability testing and patching. And I also have a microphone now. And we have a mix of talks from the technical track, journal first papers, demo papers, and I believe all of them should be in-person presentations. We're missing still the SSP catcher presenter. Do we have SSP catcher? All right. Hopefully everybody will show up, but let's get started. So as a reminder, everybody has, so longer talks have 10 minutes for the actual talk and 5 minutes for questions. Short talks, 5 minutes for the talks and 2.5 for questions. So with this, let's welcome the first presentation. So whenever you're ready, please start. Looking forward to it.
Okay, good afternoon, everyone. I'm Jiamou from Data 61 CSIRO, and today my talk is a silent vulnerable dependency alert prediction with a vulnerability key aspect explanation. And basically, we want to combine the explainable information with the traditional binary detectors for the patching detection. And the open source software is cheap and convenient, so it is widely used in different software. But at the same time, the vulnerability is widely spread, and the vulnerabilities like the WannaCry and Log4Shell can cause losses of billions of dollars. So it's important for the OSS downstream users to get notice about patching in time. And currently, people rely on the public adversary database to get notice about disclosed vulnerabilities, like showing on the left. It is a screenshot from the NVD National Vulnerability Database. It contains lots of descriptions. Those descriptions contains lots of basic information about vulnerabilities. And it also has related GitHub links, so the user can have noticed about the vulnerability and the patch updates. And on the right is another adversary database, the GitHub adversary database. It also has the similar things and also has the GitHub links of the patching. And the issue of those adversary databases is the silent patching. And here is an example. It's a patch of the Linux. It was fixed on the September 22nd, 2016, while the corresponding Xiwei record was published on the November 15, 2017, which was a year and 2 months later. That is because a lot of maintainers, they consider the benefits reasons, so they choose to silently patch the vulnerabilities. And to solve this, the previous work also contains a work in 106 just now, if you listen. They train the OSS vulnerability predictors by the machine learning automatically and with the input of the commit messages and code changes. The problem is they do not have the explanation, so the user still have to double check the codes and manually analyze the characteristics to decide whether to adopt or reject those detections, which can easily overwhelmed by the number of alerts. The explainable AI becomes popular right now as it not only gives an overview to the model's decision, but also allows users to view more possibilities of the questions and gain more understanding after working with it. It has been used in many domains. And noticing its importance, the GitHub also uses it. It has an app named CodeQL. It uses rules and machine learning to detect vulnerabilities, and it will, as shown on the left, it gives you the severity, the vulnerable code lines, and the explainable information. The problem is CodeQL first is a black box. We do not know the details, how performance is the machine learning model and what kind of rules they use. And the second problem is the CodeQL is for the maintainers, so it cannot solve the silent patching problems. And on the right is a dependent bot used by the GitHub to give the dependency alert. When the upstream software get updated, you will receive the message. But as you can see, there's no information. It is not specific for the vulnerabilities, so it still cannot solve the problem. And noticing the needs, we want to combine the explainable information with traditional binary detectors to give more information to the downstream users. And here's the overview. We collect explainable information from the MAD and the IBM X-Force and use extractive extraction methods like the name entity recognition to extract the vulnerability key information, which we call key aspects, and use the encoder-decoder model to generate them. Here we focus on those 7 key aspects as explainable information, including the product, the vulnerable version, the vulnerable components, vulnerability type, root cause, attack vector, and the impact. They are proposed by the security experts and widely adopted by different platforms. And those things, you can find their definition in the Meter CVE template. We use a BERT-based model like the name entity recognition to extract well-formed words, including product version, vulnerable components, and the vulnerability type. And use the question-answer model to extract free-formed phrases like the root cause, attack vector, and the impact. And we use the encoder-decoder models to generate explanation. And for the classification, we just add a softmax layer to the encoders. To evaluate the work, we propose these questions, evaluate the effectiveness of the classifier, the generator, and the usefulness. Our dataset includes more than 1 million commits collected from the 2017 GitHub repositories, with around 9,000 commits are vulnerable patching commits, and the rest of commits are the non-vulnerable patching commits, crawled from the same repositories. And we use AUC to measure the model effect. For the evaluation, we test both the input combinations, and we also test the different model baselines. The input variation includes the use the commit message only, use the code changes only, and use both of them. And we found both of them get the best performance, as both the commit messages and code segments can contribute to the vulnerability detection. Actually, we remove any things like the CVE ID from the commit messages to avoid the cheating of the model. And for the baselines, and we found the pre-trained model like the CodeBERT and the BERT get far better results than the non-pre-trained models, and the CodeBERT get the best results for the pre-training. And the results are similar for the generator. Still, both the commit messages and code changes can contribute to the information generation. And still, the CodeBERT model gets a better performance than the others for the generation. And we conduct a usefulness study. We propose 6 commit questions. In those questions, we gave the participants the commit messages, code changes, original code repositories, and we want them to confirm whether the commits are patching or not. And for the control group, they can only see the results of the classifier. But for the experimental group, they can see the classifier and the explanations. Here, the task 1 to 4 are the true positive, so they are the true vulnerability patchings, and the task 5 and 6 are the false positives. So we want to see what will happen. And here are the results for the participants using our tool. And for the true positive results, they get answers faster, have better answer correctness. And for the false positive, actually, they have a little bit worse performance compared to the control group, because they have to spend time to reject the wrong explanation, the explanation of the false positives. But compare with them overall, the differences are not very large. I mean, for the false positive generation, although the experimental group a little bit slower, but they do not slower very long time. Yeah. And we also record their difficulty and their comments about usefulness. And the experimental group rates the task difficulty lower, and they think the explanation most of the time is useful, because they actually they have a target to find to analyze the code. And that's all of my presentation. It's question time. Thank you.
Thank you very much. So we have some time for questions. So very interesting work, and I can see it being quite useful in practice. So I was actually wondering, as I guess putting my small developer hat, like, have you reached out to dependable developers or any other tool builders, to?
That's our next step, but get contact with them sometimes can be difficult. So,
yeah, of course. But okay, that's great. Any other questions? And have you also tried to deploy this on I don't know, maybe on some of the code bases that you are writing, so that you kind of like get this experience, not for for direct experience here on how developers would adopt this.
Yes, that's also in our plan, but this area is quite competitive. Every year, lots of work, they emerge, and we plan to emerge those things. We want to embed these things to our website.
All right. Any other questions? Okay, if not, let's thank the speaker again. And
good afternoon. My name is Lyuye from Nanyang Technological University in Singapore. The work I'm going to introduce today is compatible remediation on vulnerabilities from third-party libraries for Java projects. We know too well that open source components are widely used in nowadays modern software projects, and also but they are not always trustworthy, because the vulnerabilities could exist in the dependencies in the software projects, as reviewed by the National Vulnerability Database. So the number of vulnerabilities also increased over years. For example, the Log4Shell has affected a large number of downstream libraries. So how do we mitigate such vulnerabilities? The software composition analysis, the SAA tools have been proposed to address such a kind of situations. Basically, it has 3 steps. First, just identify the open source components, and then detect the vulnerabilities inside the components. And third is remedy the vulnerability from the user's project. Basically, there are 2 requirements for the remediation. First, fix the vulnerabilities, and also maintain the backward compatibility. And generally, the first two steps were well implemented. But the third step has various strategies and implemented differently in the modern SAA tools. First, introduce the concept of how do we do the remediation. Basically, more commonly used is a version adjustment. Basically, just upgrade or downgrade the vulnerable version to a secure version. And why do we not use a patch here? Because the patch usually works only in the source code. But the dependencies in the Maven context are usually used as a bytecode in the local repository. So we cannot directly apply the patch. That's why we also use a version adjustment. Here's an example of the remediation. It's an upgrade suggestion by the dependent bot, which is commonly used in the GitHub community. And in this case, it suggests to upgrade the spot box from 4.2.3 to 4.5, which is a minor upgrade, and it's supposed to be backward compatible. But the developer still finds some breaking logs after they build their projects. So that's why this developer turned this pull request off. It's noteworthy that the dependable also provides some compatibility score here, but in this case, it's unknown. And actually, it's unknown in lots of cases. So to propose our own approach, we first study the state-of-the-art remediation tools. Here's the results of the 4 tools that we included in our pre-study. First is a study, which is a widely used and studied academic tool. and then the dependent bot, and we'll also include 2 other commercial tools into the study. The only 2 things to notice, the first is a fixed level. Study can perform the remediation on the entire dependency graph, but the rest can only perform on the direct dependencies, which is not enough because it cannot cover all the vulnerabilities in the transitive dependencies. And the second is only steady and dependent bots, they take the compatibility into account. But steady use like a reachable remaining class percentage after the upgrading to indicate the probability of compatibility assurance, which is not always reliable because it's a probability. It's just for the reference. And dependent bot use the test passing rates from other repositories to also indicate the probability in the current repositories, which is not always reliable and sometimes can be unknown in the previous example. And to also design our tool, we also give another pre-study to study why some pull requests are rejected by the developers. And we want to know what are the users concerned about. So first is duplication. Duplication is out of scope because it's just superseded by another pull request. The second is the compilation or test or CI failures, which because of these failures or breaking changes that already happened, so developers turn the pull request off. And third one is incompatibility concerns, which means the breaking changes have not happened yet, but the developers are worried about these breaking changes. For example, it could be a major upgrades, so it could be breaking, so they turn them off. These 2 reasons account for over 50% of the rejected PRs, which means it's a pretty primary concern. The rest is just minor concerns. The comparison will also study the accepted PRs. Because we have no idea why they are accepted, we can only study the distribution. So in this case, the minor and patch upgrades, they are supposed to be compatible. The rest are not, there's no guarantee. So these minor and patch upgrades, they count for 86%, which means that in the remediation suggestion, the major or the pre-release upgrades are likely to be rejected. So we better suggest the minor and patch upgrades. And so here comes the requirements for our tool. So we first want to fix as many vulnerabilities possible and also maintain this backward compatible. And in the meantime, we want to introduce as few major and pre-release upgrades as possible to better maintain the compatibility. And to achieve that requirements, we are facing such challenges. First is the trade-off between the security and compatibility during the decision making. Because not always the candidate versions are not always both secure and compatible. So sometimes I have to do some trade-off. Also, the time complexity increases exponentially because we have to traverse all the potential solutions in the dependency graph. For example, each node has several versions, and the entire graph could have a lot of potential solutions. And also, there are another ripple effect we defined in our paper. We found that this phenomenon could also affect the results because let's take examples here is the dependency at the upper level. If you just change this version, the default version or the optimal version for a lower level, for dependency for a lower level, can be changed. So the optimal solutions are dynamically changing when you are doing any change to any node in the dependency graph. So we further formalize our this problem into a optimization problem. So we first want to minimize the remaining vulnerabilities. That's our objective, and then define a constraint. We want it to be backward compatible, so the incompatibility should equal 0. And here's the overview of our tool. We first generate a dependency graph and a call graph for the reachability analysis, and then we partition the dependency graph into subgraph to reduce its complexity. And then inside each subgraph, we use the SIM solver to optimize the objective. In case of any dead end, we have the tool will go backtrack to the previous nodes in the dependent graph to attempt other potential solutions. First, the partitioning. We have two kinds of partition. First, the vertical partition, which on the left, it just splits any subgraphs that are not connected with each other into multiple subgraphs. Because theoretically, they have nothing to do with each other during the remediation, so they can be done concurrently. The second is the horizontal partition. Because of the high complexity, so we are not conducting the remediation on the entire dependent graph. We conduct on 2 levels at a time. So it's like basically like sliding window pattern just from the top and move 1 level by level down until we traverse all the dependencies in the graph. And we further break down the compatibility constraint into the syntactic breaking and the dependency conflict, as we found in the previous study. The syntactic breaking can be detected by the existing API checkers incorporated with the reachability analysis to make sure there is no incompatible API as a code. And dependent conflict is a common issue in Maven ecosystem. We also design some rules to make sure it won't be triggered. We also introduced some other secondary objectives, like we want to minimize the major upgrades and also the pre-release upgrades in our final suggestions. Let's take an example of the optimization. On the right is the dependency graph, and 1 is the root, and we take library 3 as an example. So the library 3 has a version tree from V1 to V7. So we first check its incompatibilities. Then we find that V1 and V2 are incompatible. The rest are compatible. And then for second step, we check the vulnerability mapping in our mapping database to find out which version are vulnerable. And we find V3 and V4 vulnerable, so the V5 to V7 are incorporated into the candidate list. And for the further pruning. And the next round is just move the 2-level sliding window down, 1 level down. But the level 3 is still in there, but it's in the upper level. And in this case, we also check the compatibility, but not against the upper root project, but against the lower lower dependencies. So we found V7 is incompatible, so V5 and V6 are the candidates. Because the V5 is closer to the original version, the blue one here. So we temporarily select V5, and in the next round, because the library 13 also depends on library 3, so we would check the compatibility again. And in this case, the V5 is proved to be incompatible, so we change our candidate to V6 because like a backtracking minor. This is primarily the procedure. General procedure of our approach. We compare our tools against the state-of-the-art remediation tools, and you can see this is our tool and the dependent bot, and also the 2 commercial tools mentioned before. Our tool could fix the most vulnerabilities and also assure the best compatibilities after the remediation. And for comparison, we also design 2 baseline tools. Baseline A always upgrade to the latest version because it's a pretty aggressive one. And baseline 2 always upgrade to the versions with fewest vulnerabilities. So in the result that our tool cannot fix as many vulnerabilities as the baseline B, but it can achieve better compatibility. Another study is an evaluation study because we sacrifice some accuracy by conducting the partition. And that partition could lead to some suboptimal solutions. So we designed another baseline C. It uses exactly the same mechanism, but without any subgraph partitioning conduct the remediation on the entire dependency graph without manipulation. So we can see the baseline C has takes much longer time than our tool with the increasing size of dependency graph.
I think we do need to wrap up. You're out of time.
Sure. Okay, it's almost good. We also conducted another study on the ecosystem and found out that over 78% of vulnerability could be fixed compatibly in the ecosystem, but it's still left unfixed. That's all for my presentation. Thank you.
Thank you. All right, so we have a couple of minutes for questions. All right, so we have one over here.
Actually, I would be interested. You decided that you want to avoid upgrades to major and development versions. But the reason for that was due to the fact that normally these are rejected by developers, right?
Yeah, and according to the semantic versioning, they are allowed to have breaking changes.
Okay.
So intuitively, people want to reject them because they're more likely to have breaking changes. And usually that's the truth. Yeah.
So and you obviously added that to your optimization problem, but when I looked into your slides, a lot of tools basically recommended less updates to major and development versions, or did I get that wrong? So I think below Coral there was Dependabot or something like that, and Coral had like 170. So if you go back a couple of slides, we might be able to see what I'm referring to. We had development version upgrade for Coral with 139 and Dependabot with just 44. Or did I understand just this table wrong? Completely right-hand side.
Yeah. You mean this one?
Exactly, exactly.
And 139, right? Okay. You mean our tools still have a lot of major upgrades?
Yeah.
You know what I mean? Okay. Because we want to avoid that, that's a secondary objective.
Yeah.
But if the major upgrades can fix some vulnerabilities, if they can fix some vulnerabilities, then we'll still consider the major upgrades.
So basically, we can see from here that a lot of these vulnerabilities you found and your tool with Coral fixes are actually upgrades to major versions. So major version yield a lot of potential for fixing vulnerabilities.
Yeah, but we also ensure they are compatible.
Yeah, definitely. But that was okay. Perfectly. Thank you.
Thank you.
All right. So I think we let's thank our speaker once again, and move to the third talk.
Good afternoon, everyone. My name is Davide Corradini. I'm a PhD student at University of Verona, and my area of research are automated testing and security testing of REST APIs. In particular, this is my first work addressing a vulnerability specific to REST APIs, mass assignment, and this work was done in collaboration with Michele and Mariano. REST APIs are the mainstream technology nowadays to interconnect systems through the web with HTTP protocol. They are adopted by Google, Meta, Spotify, and so on. And they are indeed used to interconnect systems, exchange data, and manipulate remote resources. One typical adoption of REST APIs is the communication between different systems, like a mobile application with the respective backend or server. And the typical operation that can be performed on resources are the famous CREOD operations: create, read, update, and delete of resources. Because REST API are so adopted and are reachable through the web, it's very important that they are also secure. This in practice is not often true. In fact, the OWASP community has provided a list of the most common vulnerability, and mass assignment is one of the top 10 vulnerabilities in REST APIs. Mass assignment originates from a misconfiguration of the auto-binding features of REST frameworks. In fact, during the development of an API, developers adopt frameworks to speed up the development. And the auto-binding works this way. Imagine to have an internal representation of the data that might be an entity class or a table, a database table like in this case, and the HTTP request and responses going through the network. Basically, auto-binding is used to automatically map values that are present in the HTTP request and responses to internal data representation. In this case, the developer does not have to manually copy the email we see here into the database, but auto-binding will automatically map those values thanks to the naming convention, because we can observe that HTTP parameters have the same name as the column in the database. Of course, some data in the database could be read-only, meaning that it should not be accessible with writing operation from the API itself. This is the case of the admin column in this example. It may happen that an attacker is able to guess the name of columns or fields in the database and can craft a malicious request that has injected a new parameter, in this case admin equal true, and if the auto-binding is not manually set to stop the mapping between this particular parameter, is it possible that, and often is this case, that it will automatically map an injected parameter to the corresponding column in the database, causing, in this case, a mass assignment vulnerability that is compromising the data in the database. What is the contribution of this work? In this work, we propose a fully automated approach to generate test cases able to reveal mass assignment vulnerabilities in RESTful APIs. And the approach is black box, which means that does not require access to the source code, so it's applicable to any programming language and any REST framework. And also we provide an implementation of this strategy on top of our tool, REST-as-Gen, which is available open source on GitHub. The approach consists of 3 steps. First, we identify, by looking at the specification of the service, the fields that are supposed to be read-only. Then we perform a generation of security test cases that aim at exploit the vulnerability. We basically attack the API under test, and eventually a security testing oracle will identify the presence of a defect, in this case a vulnerability, as a deviation from the expected behavior, which is a safe interaction. To identify in particular read-only fields, we have a lot of automated mechanism in place. Everything starts from the specification of the service, which is a formal document describing the operations available and the parameters that they accept. For example, let's consider a very simple API that has a post operation to register a user. It has also a get operation to retrieve information about a user, and a third operation to create a book, because this example is a library API. Read-only fields are, of course, peculiar to the resource type, to the entity they belong to. For example, a user might have particular read-only fields, a book might have different read-only fields. To automatically infer those fields, the first step is to cluster together operations that operate on the same resource. And this is done with clustering, of course. In this example, we have the first 2 operations that are clustered together because they work indeed on the user. And the clustering algorithm measures the similarity between operations with the number of common parameters. In fact, you can see that the first 2 operations have many parameters in common, email, username, and password, while the other cluster, the yellow one, does not have parameters in common. After clustering, we classify every operation in the cluster with the semantic of CRUD, operation that write data. In this case, the first one write some data because it's a post operation used to register a new user, while the second one is a read operation because the adopted method, HTTP method, is get, which is typically used to read the data. And it's quite easy to compute the read-only parameters in this case with a simple set difference. We can see that the admin parameter only appears in read operation and not in write operations. Once we identified all the read-only fields in the API, we can start generating test cases that perform a mass assignment attack. So they try to exploit a candidate vulnerability. And those test cases are derived from abstract test templates. In fact, we provide a collection of abstract test templates like this one. They are manually provided, but automatically manually provided once. We already done the collection, and they are automatically instantiated. In particular, in this case, we create a user by injecting an admin parameter, and then we read a user. Why this sequence of operations? Because their execution trace will be analyzed by the security oracle. For example, for this sequence, the generated test case will have the injected parameter, and the second request will be responded by the API with the information about the user. And in this case, we can observe that the value provided in the request is present in the subsequent read operation. This means that the attack contained in this request was successful. And in fact, the Oracle reports a vulnerability. We performed an empirical evaluation of this approach in terms of accuracy of the first step, the identification of read-only fields, accuracy in general of the whole approach, so the revealing of the vulnerability, and finally in terms of scalability. In this talk, I will only present the first two because of the limited time. We constituted a set of 5 case studies. They are REST API in various languages and developed with different frameworks. And according to a manual ground truth that we compared against the automatically inferred information, we can see that the approach is quite accurate, both in determining the CRUD semantics, so what kind of semantics do operation perform, like read or write, and also the clustering is quite precise. Moving to the general vulnerability revealing accuracy on the same 5 APIs, we first run our approach on a safe version of the API without vulnerabilities. And we can observe that no vulnerabilities were detected, so no false positive, and that's a good thing. While instead on a version of those API with vulnerabilities, some of them already become vulnerable, some of them are instead, we manually seeded some vulnerabilities. We can see that also in this case, the approach did not reveal any false positive, and it's quite precise at revealing the vulnerability. In fact, all the vulnerability it reported are true, and in most cases, it was able to reveal all the vulnerabilities in the APIs. One only case is the OWASP API, for which we couldn't detect one vulnerability because the instantiation of the test sequence was not able to complete because of some parameter value generation problem. To conclude, this is the first work in the literature that addresses a REST API specific vulnerability. The best part of the approach is that it's totally automatic, so you just need to download our tool, run it on your API, given that you have a specification of the API. And we are currently working on developing new approaches for other of the top 10 vulnerabilities defined by OWASP for APIs, and we're also performing a study to empirically assess testing results. This is all for my presentation. Thank you.
Thank you very much. So we have a few minutes for questions. All right, we have one in the back.
Hi, thank you very much for the presentation.
Thank
Does this strategy work for any particular language or the framework, or like is like framework agnostic?
Basically, being a black box, we just interact with the API through HTTP requests. So the API can be developed in any language and with any framework. And we can apply the approach anyway. We just need the specification of the service which lists the operations available and the parameter that are needed.
Any other questions? So is it, I guess as a follow-up question to that, is it difficult to get this API information? I mean, what prevents you to to extend your evaluation, let's say, from, a few, I don't know, I think you had like 5-6 subjects to, let's say, like 600.
Yeah, so first, when we collected the case studies to run our validation, we had to remove public services because we cannot attack a public service that may be vulnerable. So we just mined GitHub for some API. The problem is that typically, specifications are provided for public services and not for open source services. And also, in order to use this approach, there must be other, for example, many APIs are read-only. And of course, if an API is read-only, you cannot write anything anyway, so the approach is not applicable. So that's mainly the reason of the limited set of case studies.
Thanks a lot, I understand. Any other questions? Can I also ask you, I was curious, when you showed the semantic inference, it wasn't like 100% for everything. So what were you missing there? Do you remember?
So the semantic inference is done with very simple heuristics that maps HTTP method to the CSIRO semantics. So get is used to read, post is used to create. Sometimes happens that developers do not stick to this convention and they just use get method to do everything. So of course we don't identify the correct semantics. Anyway, we are currently working on a machine learning based approach to identify the semantics of an operation not based on the method, HTTP method, but on other features.
All right, sounds interesting. Thanks once again. Thank you. And let's move to the next presentation.
Okay. Good afternoon. I'm Zhang Yun from Hangzhou City University. Today I will introduce our tool Patch Match, which can locate patches of open source project vulnerabilities. This picture provides the evolution of vulnerability numbers reported by the CVE website since 1999. The data clearly shows an overall increasing trend in CVE counts, and especially after 2016. However, at the same time, the security patches used to address vulnerabilities have not been effectively implemented. And when a vulnerability is identified, finding the corresponding patch becomes increasingly challenging due to the time gap, as the patch often gets lost among the numerous new code commits. And many vulnerabilities in the CVE and the NVD website may lack clear associations with commit IDs for the patches. On GitHub, patch descriptions often only contain the textual explanations of the vulnerability, and in certain cases, developers may even fail to provide any descriptions at all. So we propose Patch Match, a tool to help developers quickly locate patches. And the Patch Match consists of two main components. The first component is the VC match model, especially designed to enable patch and vulnerability matching. It forms the backbone of our system and ensuring accurate and efficient pairing. The second component is front-end assistance to enhance the usability of VC match and incorporating supplementary functionalities. And we collected a large amount of vulnerability information from CVE website and the NVD website, and extracted open source software related commit information from GitHub. And this data were used as training data of the VC match model. When dealing with textual data, we use two methods to construct features. The first is manual feature, which consists of 4 dimensions. They are lines of code, identity, location, and token. And the second is deep test features. We use BERT, one of the state-of-art pre-trained models, to generate the encoding features of vulnerability description and commit message. And we employed 3 models to train and fit the data features. They are XGBoost, LightGBM, and CNN. Each model was trained independently to capture different aspects of the data. And then we employed a voting rank method to perform model fusion. And then we stored the textual information about vulnerabilities and code commits into the backend database concurrently. And this is the table we use in MySQL to store the data. The homepage of the patch match shows the CVE information, commit information, and lists of commits and CVEs. The CVE information page provides an integrated display of the degree of risks and the number of CVEs and some other details presented in a visual chart format. The layout provides developers with an overview of the information. And in the information display page, we present the information of CVEs and commits in a common list format. And it includes standard functionalities such as querying, splitting, and adding. And users can also view the details of each item. When a patch is missing for a CVE, patch match highlights the details button in yellow. And the developers can interactively navigate to the model prediction page and use the VC match model for patch pairing. This is the prediction page of patch match. Developers can click on the Predictor button to perform patch ranking prediction. And when the prediction is completed, the right side of the page displays a sorted list of commits. And the developers can also switch the number of commits in the list by the top M section. And by clicking the Details button, developers can inspect the detailed information of each commit to verify the presence of the corresponding patch of vulnerability. And then they can confirm by clicking the Check button. That's all. Thank you for attention.
Thank you very much. We have time for a couple of quick questions. So we have one in the back.
Hi. What happens if patch is done in multiple commits? If there isn't like one commit, but because it was fixed like with multiple commits?
Sorry, can you describe it again?
Like there is some kind of vulnerability and multiple commits are needed to fix it, or somehow the developers decided to do multiple commits. What happens then?
What if you don't have just one patch?
Yeah.
What if the vulnerability is fixed multiple patches?
A vulnerability match multiple patches. Maybe I need to discuss with the first order in details, and maybe you can send an email to me, and I will answer you in a detailed way.
Don't have an answer. I was just interested what might happen then. Thanks.
Thank you.
Right. Any other question? So have you looked at the precision, the accuracy, false positives, false negatives?
Yes, but due to the time limited, so I don't show it in the PowerPoint.
Is it different across languages?
Mm-hmm.
Does it differ with the programming language in which the system is written?
Programming language is. Sorry, I can't understand.
I'm saying, yeah, I was just wondering if you see differences in your results, in the quality of your results depending on the programming language. Because you support multiple programming languages, right?
It's what is Java.
Oh, it's only for Java?
Yeah.
Oh, right. Sorry, I missed that bit. All right, thank you very much.
Thank you.
Okay, let's thank our speaker once again.
Okay, thank you. I'm Giorgio Di Tizio, and today I will present our work on software updates and software in advanced persistent threats. So we often hear that software updates are a critical action we have to perform to reduce the attack surface of our network and thus reduce the risk of being compromised. And this obviously makes sense if we think software into isolation. However, for organizations that have to manage thousands of machines with different software, this can be a problem. Indeed, updates often mix security patches and new feature or modification of features in a software that are used in production, so for the productivity of organization. So the organization potentially updating risk of breaking some functionality that are useful for their productivity. So enterprises are left with this dilemma of either trying to keep the pace of all the updates that arrive for their software and with the risk of breaking something, or wait some time or even ignore some updates and take instead the risk of having a not updated software version with the risk of being maybe attacked by someone. And what we found out looking at data is that many organizations tend to prefer to not update immediately, from waiting some delay or even skipping sometimes updates from 1 week up to several months. And this from security point of view seems pretty irrational, in particular if some of these organizations that are pretty big can face very sophisticated actors that are advanced persistent threats. They are basically performing targeted attacks, exploiting complex vulnerability, typically 0 days, so vulnerability that the vendor is not aware of. So we started looking into how software updates and if software updates are actually helpful. And so the first problem we found out is actually that we lack data about the APTs and their attacks. So we first tried to get a global view of the APT ecosystem, and we collected data about more than 350 campaigns over more than 10 years, and we collected information about when this campaign happened, which software vulnerability were exploited, which were the affected software, as well as other information. And from this data, we started looking into the characteristics of APTs and how this relates with software updates. And the first things that we found out is actually how they compromise the network. And the first thing is the attack vector that they employ. Typically, they employ spear phishing attacks, so typically sending emails. And what is interesting is that they employ it with or without, obviously, software vulnerability, and they prefer this kind of attack vector compared to more sophisticated attacks like drive-by or supply chain that we often hear in the news. But even most importantly, we found out that more than half of the campaign we were able to collect are actually not exploiting software vulnerability at all. So actually keeping your software updated does not help in more than 50% of the case for this kind of attackers. Obviously, it could be the case that a good software update strategy helps for the campaigns that exploit software vulnerability. So we started looking into this part of the attacks. And indeed, we found out that APTs tend to prefer to exploit publicly known vulnerability at the time of the campaign, while just a minority of the class of the campaigns we observed, so the red one and the yellow one, are exploiting vulnerability that we are not aware of publicly, or even the vendor were actually not aware of, that are the, let's say, the red one. And another key finding is that most of the APT tends to prefer the very same vulnerability. So what does it mean? That potentially software updates can help in addressing the majority of this campaign, but it's still unclear actually which approach is more cost effective. And so we looked into some software update strategies to see which one works best and what is their cost. We considered an ideal strategies, that is more or less what we heard to do. Update as soon as a new release arrives. We know that these should provide the optimal lower bound that an organization can do to reduce the risk, but we know that this is something that is pretty impractical to perform consistently. And then we compare with other approach like the industry strategy, that is more or less what organizations are doing. So trying to keep the pace of the updates, but waiting some time to, for example, perform regression testing and check that nothing breaks. And finally, we compare with a reactive approach, a more relaxed approach that basically updates the software only when a publicly known vulnerability is released. And if we see on the graph, obviously the ideal one perform the best. We have the lowest risk of being compromised, but it comes at a high cost in terms of updates. This is just for 5 software products, and we know that this is simply impractical to keep over time. But the most important finding here is that the risk profile of the industry and the reactive is actually more or less the same, but the reactive one saves you from more than 30% of the updates. So basically updating only on the publicly known vulnerability is what you should do, and the rest is actually calculated risk. So to summarize what we did, we built a structured and manually verified database of APT campaigns based on data more than 500 technical reports, and then we developed a methodology for quantitatively investigate the effectiveness of different software updates. So the key findings are 2. The first one is a good understanding of what are really APTs. Not all APTs are that sophisticated as we heard from the news. Most of them actually prefer simple attack vector like spear phishing and prefer to exploit known vulnerability. And the second one is that you can actually just be reactive on the publicly known vulnerability when you want to update because this is the rest of your action is just useless in reducing the risk. And our APT database is open access, and you can find it at this link or scanning the QR code. Thank you.
Thank you very much. Any questions? So can you say a bit more about the reactive approach? Like, what's the delay that
basically the delay that we did compared to the industry is the same. So it's basically when you start acting. So the industry simulation, let's say, of the strategy, start acting when a new update is available. And it will wait, in this case we simulated different interval, 1 month, 3 months, 7 months. It waits 1 month before actually implementing to check that nothing breaks. The reactive is the same, but actually the starting point is when a publicly known vulnerability for the current release is available. So we typically have a delay. Sometimes it's complicated to see the interface. Sometimes the release of an update happens before the publication, sometimes not. So we wanted to see if there are differences, and actually they not.
Very interesting.
You can actually ignore many of the updates for risk reduction of the class.
Very interesting. Thank you. Any other quick question? By the way, in what the journal is this published?
Research on software engineering.
All right. Thank you. Thank you very much. So, do we have? So let's thank the speaker once again. First of all.
Okay. Good afternoon, everyone. Thanks for still being here on the last session and last talk of the ICSE 2023. My name is Zhao, and I'm a principal researcher from the Waterloo Research Center in Huawei, Canada. It is my pleasure to represent all the co-authors to introduce our work, the color funda. I guess some people may be confused why we care about the vulnerability fix and what is the silent fix, why the explanation is so important. So before we dive into the detail, please let me first give some background. So first, it is about the vulnerability disclosure. The coordinated vulnerability disclosure, CVD, is commonly adopted in the OSS community. The CVD is a trade-off between the full disclosure and the non-disclosure. Following the CVD, a vulnerability is disclosed to the public only after the responsible parties have been allowed sufficient time to patch or remediate the vulnerability. Here's a common process of the vulnerability management following the CVD. The vulnerability is first discovered, confirmed in private, and then be fixed, and then the patch is integrated. Then the vulnerability is finally publicly disclosed to the security adversaries, for example, the NVD. Note that the delay between the fix and the disclosure is 1 week in median. And then the downstream OSS user monitor the security adversaries to sense the vulnerability and then apply the patch. In order to comply with the CVD, the vulnerability should be fixed silently. It means that the commit message and any other comment should not indicate the vulnerability information. From this example, we can see that the message just describes what is changed. However, since the patch is submitted to the public repository, everyone can access it, including the potential attacker. The attacker can infer the vulnerability from the code change and develop the exploit to conduct the attack. Hence, the disclosure latency extends the exposure window of the vulnerability. Here's a further example shows the potential risk caused by the disclosure latency. This is a remote code execution vulnerability in the Apache Struct project. It was discovered and reported privately on April. Then after 2 months, the vulnerability is fixed and submitted to the public repository. Note that the commit message did not leak vulnerability information. Hence, it is a silent fix. After that, the new version of the struct, which integrated the patch, is released, and the vulnerability is disclosed. We can see that there's around 2 months latency between the patch and the disclosure. One thing need to be mentioned is that this vulnerability is highly similar to a prior vulnerability in the struct project on 2017. The difference is that this vulnerability caused a data breach, which affected millions of Equifax users, resulting in a loss of more than $6 million US. So back to the vulnerability in the 2018, we can imagine that the struct users were exposed to huge security risk during that 2 months. Hence, it is crucial for OSS users to be aware of the vulnerability fix as early as possible, so that they can start the remediation process at the early stage. Our prior work, VulFix Miner, is one of the SOTA in detecting such silent fix. However, identifying silent fix is just the first step. The explanation of the fixes is also important. Here shows the timeline of the Log4Shell vulnerability. It is first privately reported to the Apache security team, and the vulnerability was disclosed on December 10. By checking their code base, we observed that the first fix is publicly available on November 29 already. And until December 6, there's already have 5 fixes exist. And with a simulation using the VulFix Miner, we find that all the 5 fixes can be detected with a good probability. However, OSS user may still ignore the alert due to the silent attribute of the fix. This is the more detail of the first fix. As we can see, the commit message is simple, and there are more than 300 lines of code changed, happen in 9 files. So it is impossible for the general user to understand the commit and further evaluate the impact. Consequently, the early alert regarding the fix will be ignored. Hence, it is important to provide the explanation. However, this is very challenging due to the 2 reasons, the limited data and the diverse data. So firstly, the fixed data is very rare. In media, there's only 0.35% of commits are vulnerability fixed. Secondly, the vulnerability related with a wide range of CWE categories, indicating the diverse causes, behaviors, and consequences, resulting in diverse patterns of the corresponding fixes. So given the extremely imbalanced class distribution and the diverse patterns of the fixed data, it is difficult for the traditional machine learning and deep learning approach to effectively learn the information from the data. So to tackle the challenge, we proposed the Colofunder, which learn the function-level code change representation from the diverse and limited vulnerability fixes to support explainable sensing. So Colafunda is a framework consists of a contrastive learner and the Funda, which is a novel approach for the function change data augmentation. So there are three phases. The Funda first increase the code change data at the function level, and then the learner leverage the contrastive learning to train a function change encoder, FCBERT. And finally, we leverage FCBERT to further fine-tune downstream tasks. The phase one is the data augmentation. Note that this is the function level code change data rather than the function level source code. There already exists various techniques to augment the function source code. For example, adding the dead logic block, switch code statement. But to the best of our knowledge, we are the first to propose the solution for the code change augmentation. So there are 4 steps in the Funda. In the first step, we conduct the function slicing on the original function and the modified function, respectively. We merge the control flow graph and the data flow graph and consider the changed variable as the anchor to generate slices. So here, we generate 2 original function slices and 2 modified function slices, respectively. And the second step, we utilize the GAN tree to generate the function change description. We consider it as a complementary information in the next step. And then in the step 3, we augment a function change by combining the description, the 1 slice from the original function, 1 slice from the modified function, and we consider such a combination as a function change sample. Then in the step 4, we further construct the sample pair for the constructive learning. A sample pair contains 2 samples which are similar either in the functionality or the semantically similar. We propose the 2 strategies here. The first strategy is the self-based strategy. Any 2 samples which are generated from the same function change, we consider them as a pair. And for the group-based strategy, if 2 samples from the same CWE category, indicating that they are for fixing the same type of vulnerability, hence we consider them as a pair, which share the same functionality. The self-based strategy is unsupervised, and the group-based strategy is supervised. Then in the phase 2, the learner tries to minimize the distances of samples within the same pair and maximize the distances between samples from different pairs. The arranger here is important. It utilizes the CWE to ensure that in a mini batch, no 2 same pairs have the same CWE. And then in the phase 3, we further fine-tune the downstream task using the pre-trained encoder FCBERT from the phase 2. So how is the performance of Colafunda in the downstream task? For the silent fix detection, the Colafunda can support silent fix sensing with the lowest manual inspection effort. The cost effort is improved by 13% and 11% respectively at different thresholds, indicating that with the same cost, manual inspection cost, we can find more silent fixes. So by tracking the performance across different CWE categories, we observe that the Colafunda cannot well handle the complex fixes. For example, for the CWE 69 and 691, the associated fix involved 2 file changes in average. Since Colafunda is trained at function level, the association between fix among files is not considered here. So we plan to further enhance Colafunda in this direction. And then for the CWE classification task, the evaluation result shows that the Colafunda improved the macro precision and F1 score by 93% and 72% respectively. We further evaluate 40 CVE without CWE information. And then our results shows that the 62.5% of the CVE can be correctly classified. As for the exploitability rating classification, our evaluation result shows that the Colafunda can improve of 54% and 46% in terms of the macro precision and F1. The key of Colafunda is that it can well learn the function change representation for the vulnerability fixes. We random select free CWE category and use the FCBird and the transformer to encode the associated fixes. And the visualization shows that FCBird groups fixes of the same CWE closely together. As for the transformer, there are much more overlap among the fixes from different CWE category. So in summary, in this study, we advocate the importance of the explanation for silent vulnerability detection, and then we propose a framework called Funda for it. Especially, we design a low-level data argumentation for function-level code change, which can support supervised and unsupervised settings. And then we demonstrate the explanation ability with the CWE and the exploitability rating classification task. Funda outperform all the SOTA in all downstream tasks. We have other free papers in the associated topic. Please check them if you are interested. For the last one, it just got accepted like 2 days ago, so we will release it soon. So I'm Jiahui Zhou from Huawei Canada Waterloo Research Center. Our team is hiring, so welcome to contact us, and welcome for the questions.
Thank you very much. So we have a few minutes for questions. All right, we have, it's close enough. I can.
Thank you. Thank you for the highly interesting talk. So it was awesome. Can you elaborate a little bit on the dangers of the technology you developed there? Because when I look at it and combine it with the knowledge we just received by the previous talk, we see that in industry it takes a lot of time for fixes to be actually employed. And if I'm thinking with a malicious mindset from an attacker, this would be the perfect part in my tool set to actually have a victim. I monitor, I know which technology they're using, and then I instantly start monitoring these technologies for silent fixes, because I can be pretty sure that there is a vulnerability if I notice there is a silent fix against it, and I know industry is slow, so I can be pretty sure the vulnerability still exists.
Okay, thank you for the question. Yes, this ethic consideration is important here. Actually, the cybersecurity is like arm race, right? Any tool is like a double-edged sword. Like the general SCA tool. The malicious party, they can still leverage this kind of tool, right? But for this work, at least we provide a tool for the general OSS user, for them, provide an opportunity for them to defend. So I agree with you. Maybe the malicious party will also use this. But without this tool, they still can do this. So at least we provide a way for the general user.
Definitely. And a security tool can be misused.
Yeah.
Thank you.
Thank you for the question.
But I guess I had a somewhat similar question. I mean, don't you, isn't the right way and the most precise way to address this just to reduce essentially the window of between, between patching and disclosure? Right? Wouldn't that be like a simpler problem rather than apply your technique, right? To kind of like work on that side of the problem.
Do you mean leverage that window to?
Yeah, so basically you're saying that one issue is that you have like this delay, right? Between until the vulnerability is made public, right?
Yeah.
Which perhaps is, the delay exists so that people can update their software. But you could also, I mean, let's say that if you thought this is basically the right thing to do, to kind of like have an immediate disclosure, and because you provide this tool, you could just try to change the policy. That's what
okay, I see. I got your point. It's very interesting that I think it's also related with what is the good practice. I believe that for some good, big company, they have a very good team, big team to maintain this, like for example, Android, LSP, right? So normally they fix the vulnerability and release disclose vulnerability like 3 months following the 90-day principle. They follow in this way because the window allow them to contact the vendor to let them have enough time to fix it, right? I agree with that. That's a very good practice, but this practice cannot be followed by general OSS, the maintainers. So actually, I advocate that for the general OSS maintainer, they should disclose the vulnerability as soon as possible. Or maybe they can switch to fix it later or maybe hold this fix until they decide to disclose the vulnerability. So it will reduce the gap, because they cannot well handle the gap unless they have a very big team to maintain all the security, to maintain all the downstream vendors. So I think the window is good, but also is bad. It depends.
Okay, thank you for your answer, and thanks again for the talk. So this brings our session to a close, and make your way to the closing ceremony.